Yes, you able to see the screen now?
Yes, sir.
Okay. Internet connection is working properly.
No, sir. That's that 100% I can understand.
Your voice is very low today.
With Microsoft Teams is
You're using your laptop or now this mobile?
orange is the laptop, sir.
Okay. Right. So display is okay now.
What, sir?
Display.
Yes, sir.
Okay, fine. Your voice is a little bit not clear. Okay. See, the basic idea is we know this angle is theta, right? It's given in the question. Angle between the horizontal and this inclined. So I have to find the angle between the vertical, or how to figure out how to take the weight components. So weight is vertical, right? And this normal is
Yes, sir.
normal to the plane. So this weight vertical is perpendicular to the horizontal, and this normal is normal to the plane. So the angle between the vertical and the normal is also theta. That's the basic idea. I don't have to figure out by geometry and all. I just have to use this simple idea that if there are two lines which are making angle theta, then the angle between the perpendiculars is also theta. Okay, here this angle is between the horizontal and the plane. So the angle between the vertical, which is the weight, and the normal to the plane, that is the normal, that's also theta. Normal, I can extend it backwards. So this angle is also theta. Is this clear?
Yes, sir.
Okay. And right. Yesterday there was some confusion with this one. See here, this, okay, you want to see here the normal reaction. There are two normal reactions. One is on this surface between M and M, and there is one more normal reaction here between the.
Yes, sir.
Okay, but you don't have to bother about this normal reaction, because you don't have to. If I write this free body diagram with capital M, then this normal reaction will come. But that's not required to solve this problem, because without that itself I can solve the problem. And if I write this equation for this, I get a new unknown, that is N1. Okay, I'm not gaining anything.
Okay.
Okay, so I call this normal reaction as N. Okay, this normal reaction will be N1. So without, just with the free body diagram of small m, I will be able to solve the problem. So the question is, a block of mass is kept in another block of mass, this one. Okay, basically we are applying a force here. So the force is very large, then the thing will start slipping. Okay.
Yes, sir.
So I'm not bothered about what is happening at this bottom surface, whether it's slipping or I don't care. I'm just seeing whether the slipping is happening between M and capital M. Okay, so that will happen if this applied force is greater than the limiting force. So the limiting force is, the limiting friction force is mu static into the normal reaction is basic, right? This is how the friction force will vary. It will increase, and the maximum limiting is the mu s into n. After it will decrease and will become, this is mu k into n. The friction force is a variable force. So the maximum friction force, I have to see whether that thing is, how it compares with this F. If this F is less than the,
Separate sheets, sir.
speak loudly.
So we do this again. That's the new sheet, sir.
Your voice is not clear.
Is it not audible, sir?
Yeah, little bit, but just till now.
So we do then again a new sheet, sir.
Okay. So the free body diagram is small m. It will be the weight, mg, normal reaction, and the applied force, and there will be a friction force here, right?
Yes, sir.
Okay. So I have to, now the voice is good. Suddenly it is going bad. So I have to compare this F with this friction force, and this friction force will vary from 0 to maximum limiting value, and then it will become kinetic friction. Okay.
Yes, sir.
So this F max I have to find out so that I can see whether the capital F can exceed this F max. So F max is mu s into n. This is a standard result. Okay, mu s is okay. Mu s is value is not given. So what is the maximum force that can be applied? Okay, I have to find the capital F corresponding to this the thing where it's just about to slip. Okay, so in this limiting condition where it's just about to slip, see the F has to be maximum, right?
Yes, sir.
When F has to be maximum, this friction force has to be maximum. Okay.
Yes, sir.
Okay, and this normal reaction is
Mg, small mg.
okay, and it can accelerate also. It doesn't have to, right? So it can move without slipping, but accelerating. This can accelerate with an acceleration A. So this equation is not correct. So this F minus the friction force see F minus F, there is a net force that is M into A. Okay, and this normal reaction is mg. Since there is no slipping, okay, I can draw the figure diagram. And for while drawing figure diagram of this capital M, I'm just considering the horizontal motion. Okay, so the force that is there in this front direction is the friction force, because this will accelerate in this direction. So there is no other force acting on capital M. So M into A is the friction force, that is mu s into M, that is mu s into mg. So from this I get acceleration. So acceleration is mu g m by m. Okay, so I have to find this is minus mu mg. From this I get F equal to mu mg is common into m by m plus 1. That is m plus m by m. Mu mg. So it's option B. It's not complicated at all. First thing is you have to draw the figure diagram of this small m. Okay, this one. So the thing is moving together, so both of them will have the same acceleration, small m, and also the capital M, because there is no slipping. Okay, in the figure diagram is m. I'm considering I have to find the friction force. So for the norm friction force, I'll get as mu dm, and n is mg. So friction force is mu mg. Okay, so the horizontal direction F minus the friction force, that is the net force, that's mass into acceleration. And acceleration I'm finding from this figure diagram is capital M. So capital M in the horizontal direction, I'm not considering normal direction. It will introduce another n1, that's not required. So just in the horizontal direction, the force is the friction force mu s into n, that's equal to m into a, and n is mg.
So capital M is moving, no, sir. It is not in equilibrium.
Yeah, it is moving. That's why it's m into a, right?
Then why have we equated to mu as m, sir?
What are the other forces acting on m in the horizontal direction? In the horizontal direction on this capital M, there is only this friction force, right? In the vertical direction, there is this normal N1, and downwards there will be no normal direction N. Okay, that will come in the vertical direction. But in the horizontal direction, there is only one force which is acting, that is the friction force. Friction force on this small m will be in this backward direction. Okay, but this capital M, it will be in the opposite direction. It's a action reaction pair, no? So the friction force on small m will be backwards, but the friction force in the capital M will be in the forward direction. So actually this friction force is the one.
So that capital F is applied only to that small m, sir, not to that capital M.
Yeah.
Force.
Yeah.
Capital. That is
Yeah.
applied only to small m.
This is friction force. This friction.
Okay.
Small f, no?
Okay, it's not.
Yeah.
Okay.
Applied force is capital F. Friction force is small f. So this is friction, and this is this dm.
Okay.
Okay. So from this capital M, I can find the acceleration in terms of.
But friction is opposite direction only, no, sir. You have written.
No, opposite in the capital M. Sorry, small m. Small m will try to slide in the forward direction, so it will oppose that. So it will be here. But this capital M, it will try to stay here itself. But this guy is pulling it. No, that pulling happens because of the friction force. Or we can say this friction on this friction force in the small m, and the friction force in the capital M are action reaction pairs. So they'll be in opposite direction, but on different bodies. See, if there is no friction, this capital M will not move. Okay, if the friction is very, very high, then the capital M will move because of the force applied to small m. So it's basically that force applied on small m, when it's trying to move, it's creating a friction force which is trying to pull this m along with it, capital M along with it. So friction force is opposing the motion of small m, but it is helping the motion of capital M. This is also a basic idea. Okay, the friction force on small m and capital M are action reaction pairs. So they'll be in opposite directions.
Okay.
Okay, and because of if friction is not there, capital M will not move forward. If the friction is infinite, okay, it's as if m and m are bolted together or joined together by Fevicol or something. Then the thing will move forward, and this forward motion is there's only one force acting in the horizontal direction, that is the friction force. So friction force should be in the forward direction for capital M. So friction force is actually keeping m and m together, m and capital M together. That togetherness will happen if it reduces the motion of small m and increases the motion of capital M. Okay, initially they are together. When the capital force F is applied, they will try to separate, right? So that separation effect can be avoided if the motion of small m is reduced and motion of capital M is increased. That's what the friction does. Friction is reducing the motion of small m, but increasing the motion of capital M, so that capital M is along together with small m.
Sir, acceleration towards rightward only, no, sir.
Acceleration is whatever the net forces.
No, sir. Capital M for acceleration. That is toward rightward only, no? Or
Yeah, both of
leftward.
them moving together. That's what I put here. It's towards right only.
So then why have you equated that MA equal to mu SN?
See, the net force in the right direction is what? This one, right? Net force equal to mass into acceleration. What are the net force?
Okay.
So here also, net force in the right direction is F minus friction. That is equal to mass into acceleration. This is
Yes,
Newton's second law.
Yes, sir.
Okay, now the voice is clear.
Okay, sir.
Better than mobile.
Okay, got it.
Okay, see, the thing is, let me introduce one more page. See, this is ground. I have one block here, second block here, third block here, fourth block here. And let the masses be M1, M2, M3, M4. Okay. The normal reaction here will be M1 into G. Okay. The normal reaction here will be how much?
M1 plus M2 into G.
Okay. So the normal reaction at this thing does not depend on the mass below it.
Okay.
Okay, so if you are standing on the ground, okay, your weight will be same as the weight when you are standing on top of a mountain. The weight of the mountain is not going to affect your weight.
Yes, sir.
Okay. So this normal reaction here at this between this normal reaction, it depends only on the small m. So this is what we saw yesterday. So let us move to today's. Okay, I send the snap of this one. So this is clear. This is a question. Okay, and you understood this one.
No, sir. You explain once more.
Okay. See, first thing is when you read the question, you have to draw the figure. So that's what I have done. So it's as if you should see. They are saying the sphere has got. There are two spheres, no? Radius 1 centimeter, 3 centimeters. Okay. So I put R1 as 1 centimeter. I didn't put R and all. Okay, I understood it's 3 centimeters. From the unit I can figure out. And the charge is -1, 10 to -3. I put Coulomb here. I didn't put any symbol and all because it's obvious that it's charged because you have to save time also. So this thing and this thing is the initial configuration, and then they are connected by a wire. So when you connect by a wire, if you have two conductors, when you're connected by a third conductor, wire is a conductor, no? So these two become the same potential. If you take a conductor, any part of the conductor will be the same potential. So if you have two conductors, if you join by a third conductor, which is a wire, okay, all of them will attain the same potential. This is a basic property. Okay.
Okay.
So the common
Okay.
potential I'm calling by V, but there will be redistribution of charge. Initial charge is -1 and 5. Okay, now it will be Q1 and Q2. Okay, so can you relate Q1 and Q2 to this initial charges?
Yes, sir. Conservation of charge.
Yeah, so consider charge. So the final total charge, which is Q1 plus Q2, that should be the initial total charge. That is 4, right?
Yes, sir.
Okay, and potential of a sphere which has got spherical symmetry, because if you see it's a spherical conductor, when you put a charge by symmetry, it will go uniformly on the surface. Means surface density will be same at all the points by symmetry.
Yes, sir.
Okay, so spherically symmetric charge distribution is equal to a point charge for points outside of the sphere. So this on the surface, it's as if potential of the sphere is same as the potential at the surface. That is same as potential at the point just outside the surface. Okay, so for the surface just outside the surface, this is equal to a point charge located at the center, and potential to be a point charge is kq by r. K is 1 by 4 epsilon naught. So the potential at this surface is same as the potential of the conductor, that is kq by q1 by r1, and similarly the potential of this one is kq2 by r2. So these two are equal. So from this I get, from the ratio of r1 and r2, I get 3 times q1 equal to q2. Because r2 is 3, r1 is 1. So 3 times q1 is q2.
Okay.
So I have two equations, two unknowns. I have to find q2 because he's asking for the charge in the bigger sphere. Okay, so I have to eliminate q1. So q1 is q2
Okay,
by 3. So this is 4 by 3. So from this I get q2 as 3. Okay, so correct option is option
Okay.
B. Option B.
Okay. So as a result of potential difference, only charge transfer occurs, no, sir?
See, the basic property is a conductor will have a uniform potential throughout its body. Okay.
Yes, sir.
Another conductor is also having its own potential. Okay, but when I join by a connecting wire is a conductor only, perfect conductor. Okay.
I'm asking if both the spheres have same potential, means then there won't be charge transfer of charge, no, sir?
No, yeah. Once it has attained the potential, there won't be any transfer. But before attaining the potential, transient period, going from here to here, there will be a transient period. No, this is the initial state, this is the final state. In between, there will be transient period. During a transitivity
Yes,
period, there will be a redistribution of charges. So that's why we have Q1, Q2 now. And
Okay,
Q2 is
sir.
Q2 is 3 to 10 minus 2. Initially it was 5.
Yes, sir.
Okay, initially it was 5, nowadays become 3. And Q1 initially was -1. Now it will become +2. Sorry, +1. Because these two should add up to 4, right? 3 and 1 should add up to 4. So Q1 was
Okay.
initially -1. Now it has become +1 because +1 plus 3 should give me +4.
Yes, sir.
Okay, so a conductor will have a same potential, and conducting is also a conductor. So when I join them, this whole thing becomes one single conductor in steady state, which will have a common potential B. Okay,
Yes, sir.
but during transient state, there will be some difference. Okay, but once it has reached a steady state, the potential will be same.
Okay. So if we join two conductors of same potential, means there won't be transfer of charges, right,
Yeah,
sir?
because it's already
Okay.
in a steady, initial steady.
Okay, sir. Okay.
So instead of -1 and +5, if the initial charges are +1 and +3, then there won't be any flow of charge because it's already in equipotential.
Yes, sir.
Okay, this one is also a basic idea only. It's sort of theoretical question. So you have capacitor. One plate will be positive, another will be negative, right? So there will be some electric field. Let that value be E. Okay, see this is air or vacuum. Okay, now if we introduce dielectric in between these two of dielectric constant K, and then what will happen to the electric field here inside?
It will decrease, sir.
By how much?
The dial.
By K. Okay, and K is greater than 1. Only then it will decrease, no? The electric field will become E by K. If K is less than 1, then electric field is increasing. Only if K is greater than 1, then the electric field will decrease. So dielectric constant is usually greater than 1. Okay, so the electric field is become E by K. So if you have a capacitor, and if you use dielectric here and a different dielectric here, okay, of dielectric constant K1 and K2, the electric field inside here will become E by K1, and here it will become E by K2. Okay, outside the electric field will be same. Here will still be E. And if there is a gap here also the electric field will be. But when it comes inside, the electric field will go down as E by K1 and E by K2. Okay, from this you can solve the problem now. What is the option? What is the correct option now? These are the options given. And K2 is greater than K1. It's given in the question. So the drop in the electric field in the second one will be more. And there is a gap here. So here the electric field is E only. So inside the first dielectric is dropping down by some factor. And in the second one is dropping down by a larger factor because K2 is greater than K1. So this is the correct option. Okay. Can you check the answer? Is it correct? Hmm. Can you check the answer? What is the correct option?
Sir,
Can you check the answer? Which is the correct option?
sir, I left the meeting, sir. Now only I joined again.
Yeah. See this question. So what is the correct answer? Is it option C?
First the number, sir.
18.
18. Option C.
Yeah. Since you understood, no? The electric field will go down by 1 by dielectric by a factor of 1 by K. And K2 is greater than K1. So here the drop in electric field will be more because K2 is more than K1. So this is the option that's matching. So here the drop in the electric field is more, right? Compared to here. The drop will be 1 by K2 here. Here it will be 1 by K1. And K2 is more, so the drop is here is more. So is it clear? Outside the electric field is E only. So between two dielectrics, here there is air only. So here the electric field is E, which is same as the electric field here. Same as the electric field here. So only inside the dielectric will drop down by factor 1 by K. Is it clear?
So once again, sir. Sir,
Yeah.
this is by factor.
Say it again.
How did you choose that option C, sir?
So the electric field inside the dielectric will go down, right?
Yes, sir.
By 1 by K.
Yes, sir.
And inside the second dielectric will go by 1 by K2.
Yes, sir.
And K2 is greater than K1.
Yes, sir.
So the drop in the electric field in the second dielectric will be more, right?
Yes, sir.
And in between two dielectrics there is air. Okay,
Yes,
so
sir.
here also the electric field will be E.
Yes, sir.
Here also the electric field will be E.
Yes, sir.
Here also electric field will be E. So inside the two dielectrics, the electric field will drop down. That's what is happening here, right? The electric field is E,
Yes, sir.
and then it's dropping down. Again, in the air it's E, it's dropping down, but the amount of drop down is more because K2 is more. So the
Yes,
dropping factor is more. Again, it is E. Okay, this is D.
Yes, sir.
So it's clear now?
Yes, sir.
Okay. Right. So, right, let me do some theory now.
So I have sent you questions over WhatsApp.
Yeah, I've not seen that. I'll see it. But most of
Okay,
them look basic only. I don't. So, just a minute. See, this thing is standard question. You know the answer of this one? Your mic is off.
Option
No, no,
13
no,
questions.
no. Do you know how to do this one?
No, sir.
Okay. See, this is a capacitor, right? Positive plate and negative
Yes.
plate. And suppose I introduce a dielectric here, say K1 and K2. What if the capacitance of this new capacitor? See,
K1, K2, epsilon naught A by D.
yeah. See, if the capacitance of a capacitor is right. Okay. So capacitance of C1 is something, right? It's epsilon naught A by D, right? Epsilon naught
Yes.
E by D. It's K1. So similarly, actually this is D1. K2 epsilon naught E by D2. So C effective in terms of C1 and C2, what is it? Actually, 1 by C effective is 1 by C1 plus 1 by C2. Is that clear?
Are they in series, sir?
Yeah, this is capacitance C1 and this is capacitance C2. They are in series. Okay, so similarly, if I have a capacitor plate like this, and if I have dielectrics like this is one. Sorry, there's the other one. So here the capacitors will be in what combination? This is second dielectric. This is K1. This is K2. So this is say C1 and C2. So here C effective will be C1 plus C2. Is it clear? Here you have two capacitors, one like this and one like this, and I have to find effective capacitance from here to here. So these two are in parallel, right?
Okay, they are same potential. Fine,
Yeah.
sir.
So they are in parallel. So similarly here, if you call this is C1, C2, C3, and this is C4. So C1, C2, C3 are in parallel. Okay, and that combination is in series with C4. Okay, so first I have to find these three in parallel, right? So it will add. So C1
Yes.
plus C2 plus C3. Okay, let me call it C series. Okay, and that is in, so 1 by C total will be equal to 1 by CS plus 1 by C4, the fourth one.
Yes, sir.
So now if we put everything in terms of K epsilon naught E, because the D is D by 2 and D by 2, and area is A by 3, A by 3, A by 3. So if you put and simplify, you get it.
Okay,
You'll try it. I'll tell you next time if you don't get it.
yes, sir.
So this is a standard question only. So I can, so instead of, if I split like this, okay, and call this K phi. So what you have to do is you have to combine these three, 1, 2, 3 in parallel, and then K4, K5 in parallel. And after that, I have to combine these two as in series.
Yes, sir.
Okay, I'll get back to this later. So I hope you know this theory part so that I can go a little bit faster. So this one, this is a cell. So this is B is usually representing the terminal voltage. Okay.
Yes, sir.
Okay. So when I connect to an external circuit, like an external resistance, the current will start flowing. In an ideal cell, the equivalent circuit is the voltage which it can provide, and the internal resistance. Internally, there will be some resistance that will actually be zero. Okay, so for an ideal cell, whatever is the cell EMF, that is same as the potential difference that will appear across its terminals. But a real cell will have some finite resistance value, and the resistance will be very small. And if it's a very good experiment, it's very, very small. So, but here in this case, when the current is flowing, because it's connected to external circuit, the potential difference across the terminal will be different from the potential of this internet potential of this cell. And the difference is E minus I into R. Okay.
Yes.
So this is yeah, this is an ideal cell where the internal resistance is being represented like this, so that I can represent as a circuit as E in series with the internal resistance. So the current flowing in this circuit will be the total voltage, that is E, divided by the total resistance, that is R plus R. Okay, so the current is different from E by capital R by an amount due to this small r. And if you have two cells connected in series, and I want to represent this combination by a single cell, and let the cell have an equivalent EMF, E equivalent, and internal resistance. This cell will have internal resistance. and let the internal resistance be R equivalent. So I have to relate E equivalent to E1 and E2 and R equivalent to R1 and R2. So you know this relation. This you already
So
studied.
R equivalent to theta, then E equivalent will be E1 plus E2 only.
Yeah, and that we can derive easily. So basically, the equivalent circuit should have the same VA characteristics across EC as the original circuit. In the original circuit, whatever is the VA characteristics across the terminals A and C, that should be the same characteristic of the equivalent circuit. So in the left circuit, the potential drop from A to C is. So I'm trying to find the potential drop from V to C. That will be E1 minus IR1, because against the direction of current, there will be a voltage rise. This you know, right? In a resistance, the current is flowing in this direction. So while going from here to here, there will be a voltage rise. Voltage will rise. Because in a resistance along the direction of current flow, there will be a potential drop, right? So against the direction of current flow, there will be a potential rise. So going from left
Yes,
to
so
right.
current will flow from high to low potential.
Yeah, in a resistor. So if I'm going the opposite direction, there will be a potential rise. So from going from left to right, there is a drop here. And the internal resistance R1 is there, which is not shown, but we are going the opposite direction. So the drop will be E1 minus IR1. Actually, it's
Yes, sir.
simply E2 minus IR2. So this I can write as E1 plus E2 minus I into R1 plus R2. So in the equivalent circuit, the drop from E to C is E equivalent minus I into R equivalent. So comparing these two equations, I can say if E equivalent equal to E1 plus E2 and R equivalent equal to R1 plus R2. Okay, so if we have one more cell, the third cell, then E equivalent will be E1 plus E2 plus E3. And R equivalent will be R1 plus R2 plus R3. Okay, so similarly, I can have n cells in series. So I can combine R equivalent as R1 plus R2, so on up to Rn, and E equivalent is also sum of E1 plus E2, so on up to En. And if you have two things in parallel, so now also I'm representing, combining these two as a single cell. So I have to relate R equivalent to R1 and R2, and then E equivalent to E1 and E2. So what is the relation? How is R1 and R2 related to R equivalent? One by R.
One by R, sorry, 1 by R2.
What about E equivalent? equivalent and E1 and E2 are not same. Okay, so E equivalent by R equivalent equal to, this is the final relation. 1 by R equivalent is 1 by R1 plus 1 by R2, and E equivalent by R equivalent equal to E1 by R1 plus E2 by R2. This is a parallel combination.
Yes, sir.
This you all should already know. Okay, this can be easily derived. So in the first circuit, you have to drop from E to C. That is this one. In this first branch. Okay, so the drop from E to C along this branch is E1 minus I1 R1. Okay, along this lower branch, it's E2 minus I2 R2. Right? So from this, I can get I1 as this one, and I2 as this one. Is it clear?
Yes, sir.
Okay, and here in this, I1 plus I2 will combine to give I. Okay, so here across these terminals, the current is I. So I have to get the expression for I. Okay, and this equivalent circuit, the drop from A to C is E equivalent minus I into R equivalent. Okay, so from this I get I as E equivalent minus. Is this clear?
Yes, sir.
Okay, and this is the relation, right?
Yes, sir.
So in that, if I put these expressions, okay, I get this one. So here I can separate the terms like this: E equivalent by R equivalent minus V by R equivalent equal to E1 by R1 plus E2 by R2 minus R2 by. So this equality will hold if this blue term is equal to this one and this yellow term is equal to this one. So when this yellow term is equal, then it means that 1 by R3 should be equal to 1 by R1 plus 1 by R2. So from this I'll get this thing, above thing is true if 1 by R2 1, and this thing will be equal if E equal by R equal to E1 by R2 plus E2 by R2. So since these thing has to be equal, so I'm getting these two conditions for the equivalent circuit. So R equivalent is related to R1 and R2 as this one, and E equivalent is related to E1 and E2 like this one. Okay. So for NEET, we don't need this proof, we just have to use this result.
Yes, sir.
Okay. And if you have third resistance in parallel, third branch, say one more branch with E3 and R3, so it will become 1 by R equivalent become one more term here, 1 by R3, and here it will be E3 by R3. Is that clear?
Yes, sir.
And so it can also be up to N also. We can have N resistors in parallel. So this is how.
Sir, if their polarities change, means
No, then it become
that is
complicated. No, then you just have to put E1 as minus. If the if E1 is 2 and E2 is 3 with the correct polarity, and E3 is 5 with the opposite polarity, you take E3 as minus 5.
okay,
Okay.
sir.
You take the polarity in the same direction, but change the value as minus.
Yes, sir.
Then you can use the same result.
Okay. We have problems now, sir, like N batteries with two batteries polarity change, and what will be that net?
Yeah. Similarly, see, you assume the polarity is reversed. Okay, with the minus sign.
Okay.
Okay, if the polarity is reversed, you make it proper, but put the EMF value as the negative of that. Okay, and then you can use the formula. Okay,
Yes,
internal
sir.
resistance of a cell is 2.1 volt, which gives a current of 0.2 amps. So the resistance to 10 ohms is. So solve this one. Use pen and paper. So this is a single cell which is connected to a resistance. Got the answer?
1 minute.
Question is clear, no?
Yes, sir. 0.5.
Yeah. So this is a circuit. What about this one? 2 amperes flows through 2 ohm resistance were cut across a battery. The same battery supplies 0.5 amps. Okay, this is also very simple. Shall we skip? You can do it, right?
I want that to work in the system. Okay.
So basically 2 equations and 2 unknowns.
Yes, sir.
Done?
1 minute. One by 3. Yes, sir.
Okay. This one. N equal resistors. Value R each connected in series across EMF E of internal resistance capital R. Okay. The current drawn is 1 amp or I. Now the indices are connected in parallel with the same battery. The current drawn becomes 10I. Okay. The value of N is. This also is a straightforward question. Again, you have two equations and two unknowns.
One. That is 10.1, sir.
Answer is
Second
10. So basically, you will have two circuits, no? So the current in the first case is this one. Okay. In the second case, the current is 10I. But when you have R resistors connected in parallel, the effective resistance is R by N. Okay. So in the second case, it's 10I equal to G divided by total resistance is R plus. So you got this equation.
Yes, sir.
In the series, it's I equal to this one. So now I have to find capital R, no? No, I have to find N. So I can divide these two. So I will knocked out and E also get knocked out. Okay. So an R is also getting cancelled. So this is how you did, right?
Mhm.
Done?
No, sir. What are the equator?
See, these two equations are correct, no? 1 and 2.
Yes, sir.
Okay. So I have to find small n, right?
Is small and okay.
The number
That's
of
one.
number of resistors connected in series and parallel. So everything will cancel if I divide, or if I divide these two.
Yes, sir. Yes, sir. N equal to 10. Okay.
Okay. One basic question. Suppose I have some resistor combination like this, and I have another resistor combination which is exactly same as this one. Plus I'm adding external additional resistance.
3 parallel resistances.
Yeah.
Okay.
Say R prime. Okay. Now we find the equivalent resistance between these two. C, A, B, and then these points B, C, and D. So which resistance will be more? Resistance across AB or resistance across CD? Which is more?
This is AB.
Yeah. So how do you understand that?
The parallel means then resistance will decrease, no, sir, by N factor.
No, but here I'm putting R prime. Here everything is R same. I'm adding a additional resistance R prime. Okay. So resistance will see when you're adding an, you can assume as if there is a additional resistance here whose value is infinite. That is same as path being not there, right?
Yes, sir.
So compared to R prime, infinite is more.
Yes, sir.
So we can say resistance of AB is greater than resistance of CD. Another way to understand is to going from C to D, there is one extra path here. Okay.
Yes, sir.
Here the AB passes whatever is there, the same paths are here. But for CD, there is an additional path here. So when you have an additional path, the resistance for going from the current going from C to D is reduced. Okay. So in parallel connection, as you add more resistances in parallel, the effective resistance will go down. But
Yes,
in
sir.
series, it's opposite. Series, if you have
Yes,
n
sir.
resistors, if you add additional resistance, then the resistance will be more than the original one. In series, if I add even a small resistance, then the new combination will be more than the previous one.
Yes, sir.
That's why the current here is 10I when connected in parallel. When connected in series, the current is less. When connected in parallel, the current is more. Okay, this one. This is also very simple. I think internal resistance. This is a kind of convection source. Okay, this is also simple. I'll skip this one.
Yes, sir.
You can check after the class. Have you download this JNT software?
No, sir. Afternoon only I got my laptop.
Okay, today evening you do it, and then once you do that, I'll put this JNT files in that Google Drive folder, so you can open this thing for revising. Because if you don't revise, you will forget. Then it's of no use. For a cell terminal potential difference of 2.1 when the circle is open and reduces to 1.1. This is also very simple. You have two equations of two unknowns. Is it clear? Just read this one.
Positive. Open circuit means that there won't be current flow, no, sir.
Yeah. So the terminal voltage will be same as the cell EMF. So cell EMF E is 2.2 then.
Yes, sir.
So once you know the cell EMF, when it's connected in the external resistance, you know what is the relation, right? In the second situation, there will be a current flowing. So the terminal voltage you can find out in the second case. In terms of cell EMF, and if you have two resistors in series, then the voltage across one of them is.
Sir, but they didn't give that current value.
So that you can eliminate. See, if you have two resistors R and capital R in series with a voltage of V, you know the potential difference between small r, right? The potential difference between these 2 points. Potential drop across VR, you know, right? Across R. How can you find out? It will be R divided by R plus R into total voltage. This was a standard result. This you know.
No, sir.
See, this is a series combination, right? R and capital R with a
Yes,
total
sir.
voltage drop of V. So the voltage will get divided as in direct proportion. So R divided by total resistance is total voltage. And what is V capital R? Its resistance divided by the total resistance. R plus capital R into the total voltage V. Okay.
Okay. No problem.
So in the second case, this is the cell EMF and internal resistance R is there and the external resistance. So the terminal voltage is the drop across this capital R. Because this is internal to the cell, no? Small r, internal resistance. This is the cell. The terminal voltage is voltage across the capital R. Yes or no?
Yes, sir.
So the voltage across capital R will be R divided by the total resistance R plus R into the total voltage that is cell EMF. So this is the answer. So capital R is 5 and internal resistance is how much? Okay. I have to find the internal resistance. Okay. Okay. So this is equal to 1.8 and E is 2.2. And capital R is given as 5. So from this I can find smaller. Can you get the answer now?
Yes, sir.
Got the answer?
Yes, sir.
Option A, right?
So, yes, sir. But once again, can you please tell me how did you write them?
Yeah. That's a standard
One
discipline. I'm going to explain that. See, here I have n resistors in series, right?
Yes, sir.
Okay, so the current will be same.
Yes, sir.
Okay, and the total drop across the combination is V1 plus V2, so on to Vn.
Yes, sir.
That's equal to I into R1 plus R2 plus Rn, because I is same. I can take it outside.
Yes, sir.
Okay, so now, and V equivalent is, in the equivalent circuit is I into R equivalent, right?
Yes, sir.
And R equivalent is R1 plus R2, so on to Rn. It's a series combination.
Yes, sir.
So voltage drop across any Ri is I into Ri. Take the
Yes, sir.
ith resistance here. Okay, the voltage of across that is I into Ri. Current is same.
Yes, sir.
So and Ri and I is V divided by R equivalent, right? From here.
Yes, sir.
So it's V divided by R equivalent is the summation of all the resistance.
Yes, sir.
So from this we can get the voltage across the resistance Ri, that's Vi. It's this individual resistance Ri divided by the total resistance into the total voltage drop. V is a drop across the full combination. V is a drop from here to here.
That is EMF of the battery only, no, sir.
Not necessarily. If it is connected to a battery, it will be whatever is the voltage. It can be part of any circuit. Okay, but whatever is the voltage drop from here to here, that will get divided among these two in the direct proportion of the resistance. So if whatever has got the more resistance value, that will have the more drop across it. Because for Ri, this V by summation of this thing is a constant, right? For R1, R2, R3, everything, because it's V divided by the sum of all resistance. That is same for R1, R2, R3, everything. Only the numerator, which is Ri, that will change from R1, R2, so on. So if resistance is more, the drop across that particular resistance will be more. So this is
So I same means then V should be EMF of the battery only, no, sir. V by R equivalent.
VI is
No. I'm asking I equal to V by R equivalent, no, so that V is EMF of the battery only, no.
no, whatever is the potential drop here. Don't talk about the battery case. In general, whatever is the potential drop from here to here, that potential is V equivalent, or we can say V. Let the battery be connected and all. That is a different thing. We can come to that later. Battery will be there. There will be internal resistance. So this V will be equal to E minus IR.
Okay.
Those things you can add later. But whatever is the voltage drop across these terminals of this combination, that will get divided in the direct ratio of the resistance.
Okay, sir.
So Ri equal to voltage across Ri is Vi equal to Ri divided by total resistance of the total voltage. But this total voltage divided by total resistance is a constant for all R1, R2, R3. So whichever has got more resistance, that will have more drop here. So if there is a total drop of 100 volts, then the resistance which has got maximum value, that will have the maximum drop across it. Okay, so in the case of two resistors, R and capital R, the drop across small r is that resistance divided the total resistance in the total voltage. This is a constant for all R and capital R. So the voltage is proportional to the resistance value. This is constant for everything. So whichever has got the more resistance, the drop across that resistance will be more.
Yes, sir.
So for this R and R should be strictly in series. I cannot have one more resistance connected like this and all. Then the same current flowing in R and capital R are not same. So it's strictly applicable only for series combination.
Yes, sir.
Okay, this one is to say. Oh, this is also very simple. Okay, it says the theoretical question. What is the answer?
1 second, sir. Slope m plus intercept e. Slope is minus r, sir.
You have to see what is the y-axis and what is x-axis. Okay, between v and I. So hopefully v is y-axis. Then this slope will be minus r. And the intercept will be e. Okay, is it clear?
Yes, sir.
You still have E of V and internal resistance R is connected as variable external resistance. Resistance R is increased the potential difference across R. Okay, this is also mathematical question. Try this one.
So first option,
We have to find R is a variable.
if R value increase means the net potential will decrease now, sir.
We have to find V versus R, no? V versus capital R.
Yes, sir.
So is it a straight line graph?
In denominator, if it is R means then it will be a curve only now, sir.
Yeah, it's a curve only. It's not a straight line. So which
Option
option?
A,
No, think properly. You have to put different values of capital R, no? If you put,
okay.
if you put large value of R, what is happening to the value of V?
Maximum value.
It's saturating to some value, right?
Yes, sir.
So it's option C. So this is the basic relation, V equal to E minus IR, right?
So if I put the minimum value, okay, that also, okay, fine, sir, 0 only.
See, this is the basic relation. Okay, and then this current I can write in terms of EMF E, this one, because I have to find the relation between V and capital R. So the EMF E and small r are fixed. Okay, so here there are only two variables. One is the V and there is a capital R. Cell EMF and cell internal resistance are constants. Okay, so from this I can get the relation. If you put R equal to 0, so it is 0. So this is the correct one. And after, if you put very, very large value of capital R, then it will saturate to E. So this relation is clear.
Yes, sir.
Okay, this one 22 batteries. This is also very straightforward.
Okay.
So there are different ways of doing this problem.
Net voltage is 4 volt. by plus line by 1/3 ampere. Potential equal to TN3.
He has given the circuit diagram. So we use that one.
So current 1/3 ampere, but I don't know how to find the potential difference.
You have to go from V to Q, right? So find the drops from P to Q. So there is a rise of 4 here. There's a drop of 8 here. And the current is there. So the opposite direction of current will be a rise. In the same direction of current will be a potential drop.
R1 value they are given. Fine.
Got it?
1 second, sir. No, sir, I'm getting minus by 1 volt.
Did you combine these two cells as a single cell?
Yes, sir, I took it as 4
Okay.
ohm.
So the equivalent voltage is 4, and you have to put the proper polarity. This 8 volt will decide this is the dominant voltage, so that will decide the polarity. So it's 4 this way, and 1 and 2 will combine as 3 series. No, so its combination is easy. You just add them. So this is the equivalent cell, right? So from that we can find the current 1/3 and drop. This is 4 is drop. 4 minus 3 into current in this circuit. So against the direction of current flow, there is a potential rise. So 4 minus 3 into the current. 3 into the current is 1. So 4 minus 1 is 3. So the drop from P to Q is plus 3.
Yes, sir.
So option is A. There's another way of doing it using KVL. You know what is KVL, right?
Yes, sir. But I
So-
should not take voltage drop across 9 ohm. No, right, sir.
So applying KVL means I have to find the drop from here to here. It's actually exactly the same thing. So instead of finding the equivalent cell, I don't have to do that. I just have to find the current. So to find the current, I'll go, let the current be this way, right? Let current be I. So in this direction, the total drop should be 0. So here there is a rise, and here there is a drop. Or I can write the KVL as potential rise equal to potential drop, right? So going along this loop, the potential rise will be 8 minus 4, that is 4, equal to the drops along the direction of current will be drop. So 2 plus 1, so 2I1 plus 1I1, that is 3I1. So I1 is 4 by 3. I'm making, sorry, 9 is there, no? So it's 3I1 plus 3 plus 9. So this 12. So from this I get I1 as 1 by 3. Right? This is by using KVL. Is it clear?
Yes, sir.
Okay. And after that I have to go dPQ I can find by drop from P to Q. So here there is a rise. So here is a drop. So it will be 4 minus 4 plus 8 is 4. And I'm doing against the direction of current. So it will be minus 10. So 1 plus 2, 3. 3 into 1/3. So 4 minus 3. So without combining the cells, I can just find the current using KVL. And to going from P to Q, I can use the summation of drops. So without
Sure.
combining cells also I can solve this problem. Clear?
Yes, sir.
This one. Two cells having same for concurrent series. This was a simple question if you think clearly. Understood the question? See, this is a circuit diagram, right? Circuit diagram is clear. Okay, so is it possible for this drop from here to here to be 0? Because going from here to here, there's a drop across this cell, right? So here there has to be a rise in voltage. That is possible if the current is flowing in this direction. Is that clear? And the current is flowing in that direction, no? So the current should be of that value such that the rise of voltage across R1 should balance the drop of voltage across this cell V1.
So I can't understand.
The circuit diagram is clear. Two cells, internal
Yes,
resistance
sir.
R1 and R2, and the EMFs are same E. Okay, so
Yes,
the
sir.
drop from this point to this point is the cell EMF E plus here there will be a voltage rise now across R1 because current is flowing this way. So across R1 there will be a voltage rise. Across this cell there is a voltage drop. Okay, and across this R1 there is a voltage rise. So the net drop from this point to this point is the drop E minus the rise IR1. Is this clear? V is the drop from this point to this point across cell 1.
Yes, sir.
Okay,
Okay.
when this V is 0, that is possible because these two terms are subtracting. Okay, and I is 2E divided by the total resistance.
Yes, sir.
So everything is known here. You have to find capital R, no, in terms of R1 and R2. So E will cancel. So we'll get this one. Simple manipulation.
Yes, sir.
Okay, there are some more questions, you can try them. So you download that software.
No, sir.
I had sent you a mail. This one I had this software. Okay, I had sent you a mail.
Okay.
From did I send? Okay, I have sent you. Yeah. This is a mail. Yeah, I will send it to you. Okay, so you just click this link and then double click it to install. Okay, so once you install this software, you will be able to open this file, which I have put in the directory in your folder. Because if you don't revise, it's not useful. If you
Yes,
forget,
sir.
then what's the point? So here your folder is there. Okay, I've created a folder JNT. That's for the JNT files. So this thing you have to download it, and then you have to open in your machine, laptop. .jnt file, and that it will open like this one. This is the file.
Okay, sir.
Okay, so we'll meet tomorrow, So the thing is, you send that, what is that thing? Batch. What is that called? You send one video, no? Batch. What is it called? No, block.
Block strategy.
Yeah, block strategy. So what
Yes,
is the
sir.
block strategy?
If we finish first block means we can get maximum questions from that one, sir.
Yeah, fine. So we can, yeah, I got it. So I was just checking whether you go to or not. So from next week, I can do that. I can follow
Okay,
that.
sir.
So from next week, I will proceed according to that sequence. So he's
Okay,
basically
sir.
saying the first block means it's easy to cover and you can also get maximum marks.
Yes, sir. Maximum questions will be from the first block.
Yeah. So from next week, I'll go according to that.
Okay.
Okay. So this week I'll just continue with this one only.
Okay.
Okay. So just download this software and then just send me a message that whether you are able to open the JNT file or not.
Okay.
Okay. Okay. Then see you tomorrow.
Bye, sir.
Okay. Bye.